People are saying. Great. Okay, very good. So a triumph of technology and perseverance. The echo is gone, I hope. Let me repeat then. People use the word mind loosely and in many ways, and we don't want to get too ensnared in semantics of people talking at cross purposes, because they're not meaning the same thing by the same word. It's not yet a proper scientific term. However, there clearly is something important in the world that it refers to. We know it when we see it, and everyone kind of agrees on certain instances of mind. The minds we're most familiar with are minds of human beings, and they can be of very different kinds of minds, different personalities. We also associate minds sometimes with fictional characters. You see Lisa Simpson in the corner there, and she exhibits the characteristics of what we would call a personality and a mind. Key properties of mind that I think we have to require of anything we want, that we decently refer to as a mind, is that it should process information, that it should be open, that is, it should take inputs from the world and produce novel outputs depending on what the inputs are. I put an asterisk there because you might say, well, couldn't you think of a brain in a vat that just thinks and thinks and thinks? Would that be a mind? Well, it would be a mind if it were generating some stochastic, probabilistic noise input that it worked from, so that it didn't just keep repeating the same cycle over and over again. So it's open in a special sense, but so if it were like that, it would qualify as a mind, I think. If it were just a black box, a computer that kept cycling through an infinite loop, I don't think we would call it a mind. And we want a certain kind of power. I mean, there are quarters of the internet in which you can find debates about whether a thermostat has a mind, but I think that's really stretching it. And for our purposes, we want to consider minds that have significant power. In fact, an amount of power that I'll make precise a little later. Now, the human bodies in which we recognize minds are not believed anymore to be the through and through the seat of mind. Rather, the mind is, for the most part, embodied in this gelatinous mass we call a brain. And at first sight, brains are rather formless. It's not clear what the structures are, that they have any organized structure. However, scientific investigation has revealed that actually it's a very, very structured organ. This is a magnificent image of an unfolded brain. The reason the human brain looks so formless and so forth is very misleading. It's actually structured as a two-dimensional object, organized as a two-dimensional object that just, in order to fit inside a skull, has to be crumpled up like a napkin inside a wine glass. This is a magnificent image from the Wellcome found collection of scientific images. This reflects an enormous amount of data. So this is not an artist's impression. This is actually an enormous amount of data of magnetic resonance imaging, that special techniques that show who's connected to who in the brain cells and the pattern of wiring, the pattern of connection in this two-dimensional object. If you know something about brain anatomy, the thing in the middle here is the cerebellum, and then basically you see the neocortex unfolded, the outside of the brain unfolded on the wings. Taking a close-up, and again, these are reflecting actual measurements of who's connected to who inside brain tissue, and imaging techniques that show actually who's connected to who in action. You find that the organization is packets and columns. So it's actually an extremely organized organ and repetitive, and this is profoundly significant, as we'll see. There's something missing, though, from that image, magnificent as it is, which is dynamics. It's a fixed image of who's connected to who, but doesn't give you the impression that a lot is going on. And there's no comparable image for that. But a few years ago at the Desert Botanical Garden here in the Tempe area, I visited an installation by the artist Bruce Monroe of Fields of Light that covered several acres with light, and the lights were dynamic and changing colors. And I think this gives you more of an impression of what a functioning brain looks like. You can see the flows of information, flows of change in an organized patterns on a planar surface. And those can be very, very complex, and they can give you a kind of mystical experience if you walk through it. There's an astonishing hypothesis that Francis Crick, the great biologist, put forward. I think he called it an astonishing hypothesis, somewhat tongue-in-cheek, but he used the astonishing hypothesis as the title of his book. And this is the statement of it, that you, your joys and your sorrows, your memories and your ambitions, your sense of personal identity and free will are in fact no more than the behavior of a vast assembly of nerve cells and their associated molecules. Or in short, that mind can emerge from matter. So far, Crick's astonishing hypothesis looks very good. People have done many experiments in neurobiology based on this hypothesis. And so far, they've been able to track all the functions that are known to occur in thinking processes to the motion of molecules. So memory, response to different sensory inputs, and so forth. Also, there's kind of negative evidence. People have, and in physics, routinely do extremely sensitive measurements of all kinds of things. And when they do that, you have to make allowances for many, many possible influences from the outside world. You have to shield from external electromagnetic waves, radio stations, Earth's magnetic field. Shaking has to be compensated, or you put it on a platform so that the shaking is minimized. Many systems have to be run very cold so that there's not noise from thermal agitation. They have to be in high vacuum and so forth. So many things to worry about. But one thing that people have never had to worry about to get reproducible results is what people are thinking nearby or anywhere else. So there's no evidence that there's anything other than the action of matter going on.
the
known
play of physical law,
the
play of known
known
physical
laws
laws inside
all kinds of matter,
including
absolutely
including
neurobiology.
So far, the astonishing hypothesis of Crick looks very good. In fact, I would go further and say that its failure would be a great discovery and would be astonishing. So if even the slightest influence of thought, a soul, if you like, independent of matter, could be demonstrated, that would be a great discovery. And at this point, seems pretty unlikely. So that's a bit about the kind of minds we're most familiar with, analyzed at different levels. We're learning that other entities that are coming into being or actually have been all around us, unrecognized, have the key properties that we associate with mind. That is openness, power, and the ability to process information. The great example of this, the most impressive example in many ways, is the emergence of what used to be called electronic brains. Now is information processing by microelectronics. This is a modern Intel chip that's very powerful. Let me show you the specs of this. This is what runs fairly powerful computers, but not necessarily even top-of-the-line computers. These are the specs, and let me point out a few highlights. Its clock speed, the rate at which it performs operations, is 3.20 gigahertz. That is 3,200,000,000 operations per second. In comparison to this, the operating speed of human brain cells is about 40 hertz, not gigahertz, hertz. So 100 million times slower. The characteristic size of the units, the transistors in this object, is about 45 nanometers. So it's only a few, the transistors and operational units are really only a few atoms on a side. This is to be compared with human neurons, which are at least 1,000 times larger. So it's more compact. Also cheaper. It costs a lot to maintain a human being. And this is $99. However, one of the limitations of this technology, actually, that's at present the main practical limitation to using it on a very large scale, make giant brains, is that it generates a lot of heat. It runs at about, even this tiny chip runs at about 130 watts, whereas a human brain runs about 30 watts. So all in all, the electronic thought information processor has a lot more raw power than the natural embodiment of mind in human brains. Human brains, however, have a lot going for them. They have very much better input and output modalities. So they have integrated, beautifully programmed sensors, which we call eyes, that are directly
go in directly into the brain, and very clever processing that's evolved over thousands of years. Thousands is, I mean thousands, I'll come to that. And also, of course, other sensory modalities, not only Aristotle's 5, but things like the sense of balance, the sense of orientation. And together with these ways of processing input, the brain is also hooked up to impressive output facilities, actuators and sensors, actuators that also give feedback sensing. This is the peripheral nervous system laid out, and you can see that even at this resolution, which doesn't show a lot of detail, it's enormously complicated and rich and controls the feet and the hands and so forth. There's nothing quite like that as far as input and output for computers at present, but it's coming. And you can see that right around campus, where little robots, which don't have impressive brains, they have the other stuff though. They do have the sensors and actuators and are good enough to deliver a pizza. Reliable. Not often recognized, but I think profoundly true, is that emergent minds are all around us, that are different from either the electronic or the brain instantiation of mind. One is corporations. If you think about it, corporations take in a lot of information, process it, and have actuators all over the place that perform operations based on processing that information. In the law, corporations are people, and that reflects the perception or the lobbying that corporations act in a way mindfully. Universities, similarly, can be thought of as minds. Sometimes minds whose different parts are at war with each other, but minds. Militaries, all these things fit into the broad definition of information processing, power, and openness. And you can probably think of more. Another astonishing hypothesis kind of brings this together, brings these different kinds of minds together in a profound way, links what they do. This was the insight of Alan Turing in the 1930s, who proposed a very, very simple sort of machine that has a stored program that tells it how to treat its input, which is a very, very simple thing. It's just a string of ones and zeros on a tape. And the program tells it, if it sees a certain pattern of sees a one, and it's in one of its finite number of states, it erases and goes to the left, or erases and goes to the right. I won't go through the details of the definition of Turing machines, but they are very, very simple, unambiguous, programmed things. And what Turing proposed, now what's now called Turing's thesis or Turing's hypothesis, is that that's all there is. That this kind of simple machine, if the tape is long enough and you give it long enough to run, can perform any kind of information processing that anything else can perform. This is the so-called universal quantum computer. Oh, universal computer, not quantum, universal computer. So that's the second astonishing hypothesis. And despite decades now of dramatic development in microelectronics, in neurobiology, and even, as we'll discuss, in quantum computers, different kinds of computers that are entering the stage. So far, this hypothesis has proved to be true. Anything that those things can do, notionally, Turing's machine would do, it would just do it slower. Now, on the basis of this idea that you could break down the process of information processing into elementary steps, Claude Shannon, founder of information theory at Bell Labs and later a professor at MIT, showed that you could reduce it to simple logical operations, and even supplied electronic instantiations of that. So you can show explicitly how mind emerges from matter in terms of known physical entities and processes. Is Turing's astonishing hypothesis correct? It's not a law of physics. It's not a standard scientific hypothesis that is easy to check. It's, I would say, more akin to the second law of thermodynamics as it existed in the 19th century before people knew how to prove it, and also understood some kind of exceptions to it. This is ultimately a question for physics. We know the physics, as I've discussed in the previous lectures. We know the relevant physics. There might be more exotic physics that would change the picture, but for most practical purposes, we know the relevant physics of the world. And so far, no one has been able to use the laws of physics and to do something that a Turing machine can't. Any kind of information processing that a Turing machine cannot do. It was thought early on in the history of quantum computers that they might do things that Turing machines can't, but now it's been established that that's not the case. Still, there's not a general proof, and you may have noticed in the definition of Turing machines that it goes step by step and only processes zeros and ones and has a finite number of states. So it doesn't have any continuity. It doesn't have infinitely small divisions. And so on the face of it, Turing's hypothesis looks very strange and counter to some of the laws of physics. However, although there's still no proof, I think the fact that I think Turing's machine is probably false in classical physics, actually, where you can make infinitely refined measurements. But in quantum physics, where there's uncertainty, it's probably true. Quantum physics introduces enough kind of digitalization of the physical world to enforce Turing's hypothesis. But that would be a very worthy thing to try to prove. And as far as I know, it has not been proved. So those are the foundations. Now let me discuss some current frontiers. One frontier is understanding brains properly at the molecular level. Crick tells us that it can be done, but that doesn't mean it has been done, and it definitely has not. However, enormous progress is being made on looking into this object with a variety of different technologies, X-rays, computer-assisted tomography, CT, magnetic resonance imaging, and so forth. An exotic one using positrons, anti-electrons, called PET scans, is another one that gives very, very good resolution by invading your brain with antimatter. And on the basis, there's a vast literature on what's been achieved with these kinds of methods. but just to show a representative result of where the frontiers are, this is a paper from Nature that announced brain scans of jazz musicians reveal language and music similarities. So understanding the dynamical or the geometry of the dynamics that's happening as people process language or process jazz music shows related patterns. That's perhaps expected, perhaps unexpected, but in any case, to actually know is quite remarkable. Besides looking at actual brains, there's been an enormous increase in experience in brain-inspired modeling and brain-inspired engineering to do information processing. So an actual neuron is something that takes inputs and, in a cartoon version at least, sends depending on the inputs, sends a signal down an axon, a digital action potential, which is either on or off. There are patterns in time to the firing. This is idealized as a artificial neuron on the right that takes inputs from other neurons, weights the sum, and depending on whether they exceed a threshold or not, produces an output or produces a graded output depending on the nature of the input. And then obviously you can wire these together. And what's emerged in recent years is that this architecture is extraordinarily powerful. So implementing these artificial neurons in multi-layer systems, using simple training rules and a lot of data, I'll say a little bit more about this later, enables things that stymied computer scientists for many, many years, like being able to recognize different kinds of faces or other remarkable feats that I'll shortly review. All have emerged from using this architecture and training on data as opposed to programming, which is quite profound. It reflects the fact that we don't understand how we do the things we do. We can't tell a computer what to do what we do. But if we just feed it data and let it implement the kinds of things that neurons do, then it learns and becomes effective in solving problems without explicit programming. So the combination of success of simple learning algorithms and simple architectures and actual scans of the brain to see that they match these architectures and are very simple in pattern to suggest that some profoundly simple principles are at work in making and organizing human brains, especially the parts that we think of as most associated with mind, that is the neocortex, this gigantic thing that humans have that lower animals, well, lower from a human perspective, don't have this gigantic bulb that you think of when you see the brain, that we saw unfolded actually has a very simple anatomy, very regular, very modular. It's almost two-dimensional. Lay it out, but there are columns. The columns are only a few. The columns in turn are organized into layers, and very few layers, like 6 or 7 layers, each of which contains a finite number of neurons, maybe 100 or 1,000. And then you get the same thing over and over again, what looks like the same thing over and over again. Layers and columns. Another thing that suggests that there are profoundly simple principles at work, are the fact that human brains, as opposed to, say, chimpanzee brains, which we think of as maybe having mind, but sort of not very impressive information processing, that the difference evolved in the blink of an eye on evolutionary scales, on scales of the evolution of life, or even more so, the evolution of the astronomical body we call Earth, in only a few 100,000 years. So that suggests, because evolution, as I'll also discuss momentarily, is a very inefficient process, that it only took a few clever innovations to make the difference. Basically, you make more of these modules and hook them up in simple ways. And as the neural nets, once you've got them wired up in a fairly simple way, in this hierarchical way, can learn things very efficiently. And we know that actual neurons use something called Hebb's rule a lot, which is the idea that if two neurons fire together, then they start to make connections and wire together. That's the way Hebb's rule is usually quoted: things that fire together, wire together. And then the brain, in that way, finds connections that are especially useful because they're being used, and it strengthens those, prunes away the ones that in an infant brain are not being used. The neural nets use a rather different approach called feedback, which I'll come to, that probably exists also in the brain, but the neurobiological evidence is less straightforward. And that's an important frontier. What all of this suggests, however, especially the evolutionary argument, the time scale, is that, and also the time scale on which this happens and the number of cell divisions that's involved, it's only a few tens of cell divisions that give rise to the human brain. And there must be very simple rules that tell it how to work, how that happens. So there's there probably several great discoveries to be made in understanding this, and then, but a finite number will crack the problem. Another frontier related to all this is machine learning. We already touched on it in different ways. Here's how a neural net works in cartoon version, the learning, how it learns things. You expose its sensors, which here are idealized as eyeballs. They're not actual eyeballs, of course, into those idealized neurons. So it sees some information that you digitize and put into the neuron, the first layer of the neurons. Then you have neurons that talk to other neurons that talk to other neurons, so-called hidden layers. In deep neural networks that do impressive things, you might have 50 or 100 hidden layers. But then at the end of the day, you compare what you want the computer to recognize with what it says it recognizes. And so there's a notion of errors. And if there's an error, then it's reported back one layer to identify the immediate cause of the error. And when that error is identified, the guys who caused the error say, okay, I'll change my connection a little so that next time the error would be less if the same thing happened. And then the next layer up says that this guy complains, why did I do the wrong thing? Why did I have the wrong? He complains to the previous layer, and they keep passing the buck. And in that way, the whole network gets systematically better. It's a very simple idea. The equations are also very simple, basically the chain rule of calculus. And this strategy called backpropagation has turned out to be extraordinarily powerful in providing a new kind of programming, a new kind of data intense, command sparse programming that has done lots of great things recently, startling things that could not have been, were not achieved despite decades of effort by programmers. Perhaps the most startling, because it was so unexpected after decades of frustration, was the success of these neural nets with a lot of peripherals and trickery at first to get to human and then superhuman levels at some of the games which were thought to be the pinnacle of human intelligence, chess, Go, these games which have enormous literatures by experts developed over decades and thousands of plays. It turns out that a suitable neural network, just knowing the rules and playing against itself many, many times and seeing what works and what doesn't work, using basically that backpropagation strategy, is now by far the best chess player in the world. And it's not even interesting for the world champion to play against the computer because he always gets crushed. And similarly Go, which was thought to be more it is more complex, but seemed even less in the range of traditional artificial intelligence, has been conquered in the same sense that the computer does much better than a world champion human, starting from scratch in about a day of heavy processing, after about a day of playing against itself. More complicated games, social game, multiplayer games, where the strategy is much less clear, are also getting to this stage in poker, or very difficult game, World of Warcraft. The computers are approaching or exceeding the best human players. A more useful application has been to the problem of protein folding, which I discussed somewhat in the previous lecture. Biologists have gotten very good at reading the genetic code, which tells which amino acid goes step by step into encoding a protein. But that's a linear code, whereas the actual proteins have shapes that are very important. And to go from the linear code to what the output protein will look like was a problem that vexed biologists for decades, and still does. But a neural net-based program again outstripped all existing programs a couple of years ago, and now is the way things are done in addressing this problem in biology. You may have visited a website called This Person Does Not Exist. If you haven't, I highly recommend it. Go to, and you will, with the click of a mouse, see image after image of what seems like very convincing human faces that are just made up. They're just fake people. And very recently, ChatGPT, a chatbot, which sort of passes the Turing test, another thing of Turing, which is, can you converse with a computer and be fooled to think that it's a human being? I think the ChatGPT passes that test with flying colors. Just to show the sort of thing it does, I asked it, what is mind? And here's its definition of mind. That's what I typed in. What is mind? And it says, the concept of mind has been debated and discussed by philosophers, scientists, and scholars for centuries. I won't read the whole thing, but just to skip to the end, ultimately, the nature of the mind remains a complex and multifaceted area of study that continues to be explored and debated by researchers across many fields. I would say that's a solid B answer for undergraduates. And yeah, undergraduates are onto this and can start to they make take-home essays a thing of the past, I think, as tests. Thinking about this, it occurred to me that if the astonishing hypothesis is correct, that mind is a emergent property of matter, and that the fact that we have learning algorithms that teach mind how to teach that minds can use to do more and more impressive things. We should think that matter can do more and more impressive things given enough time, even with very simple operations. And look outside and you see that that is indeed the case. So suddenly the existence of life from this perspective, seems maybe not so surprising. This, given 4 billion years, even a very inefficient learning program, what we would call a slow genetic algorithm in computer science, starting from simple molecules, can start to produce this stuff. The animals, plants, the ducks, everything you see here. What do I mean by a slow genetic algorithm? Well, the algorithm of evolution, to simplify only very slightly, is you produce organisms and they live their lives, and the output is how many offspring they produce. You're not getting a lot of information back, but creatures that produce more offspring thrive, and eventually you get the bags of molecules get better adapted to the world, better able to reproduce themselves, and this is what happens after 4.5 billion years. Another frontier that sounds really scary is man-machine hybrids. And it is kind of scary, as this shows you. People are changing into creatures that really are hybrids, where they have extended minds that are used for a variety of purposes. They function in a different way than people without these devices. They can access information all over the world. They can, of course, use it to access their friends and so forth. And it's very addictive. I'm pleased to see that nobody in the audience at the moment, at least, is doing this. That's very untypical of this kind of situation. I recently have become a hybrid with the iWatch. It tells me that I have to move. It rewards me if I do the exercises, and I can set the time, I can see how fast my heart is beating and so forth. In other words, I have an extension of myself that gives me different kinds of input that I can't corrupt so easily, and also senses things that I don't normally, I'm not normally aware of, keeps better time and so forth. And this kind of coaching and nagging, I think, is an enhancement of life overall, and it's certainly a change of life. So we're man-machine hybrids. And this is a beautiful example where you start to ask, well, who's in charge here? Especially pointing towards the future. This is a human being using a computer to make better computer designs. So it's a kind of symbiosis. Is the computer designing itself, or using the human as a tool to improve its progeny? What's going on here? It's a symbiotic relationship. Both are benefiting from it. This is partly an ASU product that people are very proud of. This is the Mars rover. And if you think about it, this is also an extension of human mind. And it's actually quite a profound, it illustrates, I think, a very profound point about the future of space exploration and populating the wider cosmos, which is that human bodies don't really belong there. It's terribly difficult to maintain human bodies outside the biosphere. Heroic efforts and great expense are necessary to get astronauts out of the biosphere for short periods of time, and they come back worse. But mind, as we've said, is potentially universal, and we can gather the information, process it, share it using these kinds of instruments. And there's no shame in that. I think putting actual human bodies out there where they don't belong is fun, I guess, and exciting in the same way that I don't know, deep sea diving is, but is not, I think, the long-term successful strategy for expanding mind through the cosmos. So those are some of the frontiers. Now let me pass seamlessly to horizons. One horizon that's taking shape is quanta and mind. The pioneers of quantum theory back in the 1920s inferred that the world is a much richer place than people thought it was before. They inferred that from a wealth of indirect clues in constructing theories of atoms. They found that instead of having structures like a solar system with point particles moving around, it's actually beautiful clouds that interact in very complicated ways. To do justice to the microscopic world, you need to analyze wave functions that live in spaces of enormous dimensionality. So if you want to have the wave function of 2 electrons, that lives in a space of 6 dimensions, 3 electrons, 9, 4 electrons, 12, and so forth. That's the dimension of the space. Okay, not the number of points, the dimension of the space is gigantic, and that's even neglecting complications like spin. So the quantum world is enormously rich and structured. Few, if any, of the founders thought that we'd be able to access this structure. It's very small after all, and very concentrated. And they weren't even sure that it was correct. It's so strange, this theory. But in the basically 100 years since, these ideas have gone from triumph to triumph. So it seems that it's here to stay, and we're starting to master it. This is a tremendous challenge because it's so darn big. Right? There's enormous amounts of information, even in a proper, complete description of small systems. So key features of quantum information is it's vast, as I mentioned. It's very delicate, though. when you measure these fine details of the structure, they get disrupted. This is sort of the so-called collapse of the wave function or the uncertainty principle, that you disrupt the information when every time you try to access it in detail. And that makes it opaque to measurement. Theory can predict it, and you can test the theory, but direct measurement is very difficult. So there's enormous richness there, but it's delicate and opaque. What do we do about that? What are we doing about that to mine this richness and do this to the world as it is? There are several frontiers of quantum technology that are growing by leaps and bounds in recent years. I'll focus broadly on three: sensing, simulation, and computation. So this is a sensor that would be literally inconceivable without understanding quantum theory. It's called, well, it's the core of it is this fluorescent nanodiamond in an optical trap. I won't try to unpack all that, but just to say, essentially, you have a tiny diamond with a little defect in it. The defect in it acts like an atom, and it's the structure of these kinds of defects called nitrogen vacancy are very reproducible and very well studied. And so you have an atom that you can put where you want it with great precision and use it to measure the quantum environment in that place. That's the basic idea. And then you can modulate its properties using a magnetic field. You can make inquiries by shining laser beams on it and see what comes and so forth. So this is a technology that's enabling us to probe conditions in very delicately on very small scales. It's useful in material science, useful in biology, very versatile new technique, and representative of several that are developing as a result of controlling the quantum world. There's a profound parallel, I think, here to exploration of outer space. This is exploration of inner space. Our human senses only belong, they were only evolved or adapted to conditions in the biosphere, which is a very narrow range of temperatures and with big objects and so forth, no quantum mechanics. People got along without quantum mechanics for hundreds of thousands of years. But that's the world fundamentally, and fortunately mind, which we do have, is potentially universal. Simulators are basically scale models of quantum mechanical systems. So you replace a quantum mechanical system that may be difficult to manufacture with something that has key properties the same, but is more amenable to study. And this can be done with maintaining the quantum mechanical nature of the thing. This can be done in a variety of ways with cold atoms. They're quite beautiful, actually. These things, Rydberg arrays, where you have arrays of large Rydberg atoms, or just very large atoms in highly excited states that you can manipulate and make inquiries to using laser light. These are basically the same idea as wind tunnels or model airplanes that you use to test possible designs, but now instead of in the macroscopic world of aerodynamics, in the quantum world that's relevant to basic chemistry and structure of matter. The quantum analog of the transistor, which is used to build a computer that handles classical information, these zeros and ones, that instead can deal with quantum information, which is encoded in something called qubits. That would take me a bit to explain, and I'm running out of time and your patience probably, so I'm not going to, but these guys can be orchestrated into making information processors that are broadly similar to electronic information processors, but so they're very versatile, they're universal in the sense of Turing machines, but they use quantum information, which is much richer, so they can be much denser and perform some kinds of operations that classical computers can't, or at least can't do as fast, I should say. So here's an executive summary of where this is. The quantum sensors are already amazing. They can be used to sense local conditions with great accuracy and many, many different kinds of conditions. Other kinds of sensors called SQUIDs are very good at detecting tiny magnetic fields and so forth. And they're getting more so every day. Quantum simulators, that is these kinds of scale model quantum systems, are already doing semi-useful things. Okay, they can mimic materials that we're interested in, and we can get their properties by looking at these scale models. And they're improving rapidly. Small but useful quantum coprocessors, that is specialized little units that do particular calculations that quantum computers are better at than classical computers, are sort of in the pipeline. Unfortunately, however, universal quantum computers are still a long way off. The information is just too delicate, and although there are no fundamental limitations, the engineering challenges are very, very severe. Okay. Another horizon is the horizon of intervening in the brain. We saw that we can map it and maybe we can understand it. What are we going to do about that? Well, there are attempts to improve mind by subjecting it to fields of different kinds. This is an ongoing area. You see, it's a little dangerous. This poor guy, you see, he's wiped out his brain. If you look at the computer screens, just kidding. But the point is that you can have a feedback where you're inquiring in your own brain and see what's going on as you do different things and understand yourself in a more profound way, potentially, and improve if there's something you don't like. And a less invasive or less, how should I say, less strange, well, maybe not so much less, strange in a different way, way of affecting human minds that's approaching new levels of sophistication and power is virtual worlds and games. And these, there are serious scientific studies with actual positive data that show that computer games can be very, very good therapies for and cognitive enhancers. And out of many articles, I picked one that had a particularly striking title and was pretty simple, and also gives you a take-home message that I hope is useful to you. 9 PC games that will make you more intelligent. So I'm sure you're dying to know what the 9 are, and this was the list. Top of the list is Minecraft, and there are all these other games which allow you to construct imaginary worlds, play with them, solve puzzles, and test your reaction times against vicious enemies. Another horizon, which has been on the horizon for a very long time, but the horizon is now getting within sight and mountainous, is the horizon of drug interventions. Already in the 1940s, I believe, maybe the 50s, Aldous Huxley wrote a classic book called Brave New World, which was the centerpiece of that was that people had become addicts to something called soma. That was their reward. Anticipating the opioid crisis, maybe, but certainly anticipating things to come, where as a result of better understanding of the brain, better understanding of chemistry, it's going to happen that there will be possibilities for enhancement, abuse, but changing the way brains work by taking pills. Maybe the most stunning development, which comes out of things I discussed in the previous lecture, is the possibility of doing genetic alterations. And as I emphasize, it's my opinion, speculation if you like, but I believe in it, that there will be simple principles that are understandable, that will be understood before long, about how brains get assembled, and then you can change it using genetic techniques. So powerful tools for sure are near at hand in all these respects, but we don't know yet how to use them skillfully. That's a horizon. We also don't know how to use them wisely. That's next lecture. So let me close with a sort of teaser for the next in this series. What emerges clearly from this discussion of mind is that there are many different kinds of minds. They're getting better. Human minds are changing, presumably getting better, but it's certainly changing, better in some metrics. But there will be others. There will be other kinds of minds that are also developing that are very powerful, and there'll be an ecology. There'll be different kinds of instantiation of the thing we call mind that does information processing, that is open, and that is powerful. So we'll discuss the implications of that much more next time when we scope out scenarios for what the future might look like. This is definitely a big part of thinking about what should be and what could be, which was the promise of the first lecture. Let me just give you a reading assignment to close here. There's a marvelous book that appeared a year or two ago by Ishiguro, famous author, called Clara and the Sun, which to me is a beautiful meditation on what the future of living with other kinds of minds might be. It's told from the point of view of one of those other minds, an artificial intelligence that is meant to be a caretaker, a caregiver, and a companion to humans. And it's told from this very, very interesting, rich, but alien point of view. And you'll enjoy it, and it'll make you think, if you enjoy thinking. So with that, I think I'll close and take questions. Thank you for your attention. And
I'll need to.
you're the moderator. Oh, yes.
Yeah, we need to share this.
Okay.
Thanks very much for that, can we say mind-bending talk. I'd like to invite people in the audience to ask questions, and also those on Zoom can type their questions into the chat. Let me kick things off with a question that I have. So inevitably, I'm going to ask you about ChatGPT, given
Yes.
the moment in history that we're in. It may be a solid B student, but I feel like have criticized it, Noam Chomsky among others, and that it's nothing but glorified autocorrect, and that the
Well,
method of machine learning is very unlike how we learn. A child doesn't have to see a million pictures of a cat to decide that it's a cat.
what is it, 500,000? I don't know. No, it doesn't
so-
see pictures. It's actual cats.
Maybe. Well, that's my question. So the word intelligence is even more controversial than mine, but in what sense would you say that this is on the pathway to genuine intelligence?
Well, I would challenge Chomsky to defeat AlphaGo at chess or AlphaZero at chess. No way. So that's one. That's a kind of rude answer. But another answer is what seems to be emerging from studies of machine learning is that things we thought were unique, very difficult, uniquely human capabilities are actually things that machines can do. And the astonishing hypothesis, another way of putting the astonishing hypothesis, in fact, is that natural intelligence, brains, is a special case of artificial intelligence. If brains are made out of matter and we understand how matter works, in principle, we could set up a computer that did exactly what a brain is doing. And would that be an artificial intelligence, or it's the same thing? It's isomorphic as far as its function is concerned. So I don't buy his objections at all. No. It's somewhere between speciesism and carbonism, things that we have to. Different kinds of minds seem possible theoretically, and now are becoming possible in practice. Yeah.
Thanks. Are there questions from the audience here? Yeah.
Not sure if you're familiar with his writing on the blog.
Yeah,
I don't know how familiar you are, but.
I'm very familiar. I've reviewed it. I reviewed it.
There's something going on perhaps at the conversion level of understanding that might be non-computable.
Yeah.
Something more recent developed like that. Curious when you first appears to think because I use the way that defining it non-computable for classical level and quantum mechanically, and you think that you need something quantum mechanics
Yeah.
to create things that are truly simple.
So Roger Penrose is a serious person. He won the Nobel Prize for work on general relativity, not quantum mechanics, and certainly not biology. And I think his views are not widely accepted, to put it mildly, in the scientific community, and I agree with that consensus. He has no evidence, zero, that there's anything non-computable that humans can do, and all the evidence is to the contrary. It's certainly true that the brain is quantum. I mean, the brain is quantum mechanical. It's made of matter, and matter is quantum mechanical. It's very artificial, actually, in modern physics to separate classical from quantum behavior of actual materials. I mean, you can talk about classical laws of physics, and I did mention that they would allow infinitely fine-grained measurements and so forth. So to do an accurate job, in principle, you need quantum mechanics, but the quantum mechanics that seems to be necessary to understand how the brains work is not kind of any far out quantum mechanics. It's the kind of quantum mechanics that chemists use every day. And that is very reasonable, actually, because the exotic parts of quantum mechanics are very delicate. And typically to do refined experiments in quantum mechanics, you use very cold systems that are in vacuum. And that's not this, you know, that's not human or animal brains. So it's very, very far-fetched, I think. Yeah. Okay.
Okay, we have a question from the chat. This is the question. Joyce, she asks, why do you think the brain shows similarities in the process of language and Java?
Oh. I'm sorry. I'm not sure what the thrust of that question is. I mean, there are two possible answers. One is, it wasn't my opinion. That was the name, that was the title of a paper that I showed, and the paper has what they interpret as evidence for that. I mean, you should just look at the pictures; they look pretty similar. But you may be asking a deeper question: why is it that the processes are similar? What's the profound reason for it? And I think the profound reason is that the brain has a limited variety of tricks, and it can repurpose those tricks for different purposes. And I showed you some of the tricks and reasons for thinking that there are not that many of them. They're just used on a large scale and over again. Yeah. And when you do that, very surprising things emerge. But once you get used to the idea that neural nets can beat you at chess and recognize things in pictures, maybe it's not so surprising at the end that, because there's no question that those things are made out of materials. They've been designed by engineers, follow the laws of chemistry and physics. And so matter can support very complex and surprisingly powerful information processing. And so there's an existence proof, and there's every reason to think that the same principles apply to the kind of matter we call brain or mind. Yeah.
Thanks. Any questions?
Oh, more and more questions.
Okay.
I think we should get a question from the future. Maybe.
Personally, do you want to use ChatGPT?
So, okay. Not sure I'm supposed to answer personal questions, but okay. Do I like to use ChatGPT? Well, I played with it a bit, and yeah, I've had fun with it. I do a lot of writing for my work, and I plan to use ChatGPT as a tool to sort of generate ideas and maybe very crude first drafts of some things, just to get a starting point. So it's fun, and I think it's useful, and it's also a moving target. It's, the versions, the preceding versions of this, which were called GPT 3.0 and 2.0, were not nearly as good, and that was only a few months ago. So we'll see where it goes, but yes, I think if you're thinking of whether you should have fun using ChatGPT, definitely yes, you'll prepare for the future. All right.
We have another question.
As you pointed out at the start, lecture, you talked about how, garden processor, the process really bad, and,
Yes,
so, computers,
yes, 10 gigahertz or 20 is sort of where they are now.
yeah, but, so, when you look at modern day machine, and compare it with humans, you can say that the reason why there's a huge difference in because of computing power, because they have a lot more computing power than we have. He said,
In some ways, yes.
in certain ways, especially when it comes to calculation, those things. So in the future, if you were to like work on algorithms or some sort of that sort of thing, that like essentially I think the brain should become over and over how computers becoming as smart as humans, like.
Oh, yeah. Well, maybe I can answer at this point. So in certain respects, the raw computing power of modern microelectronics does outstrip neurons or human, but brains, as I said, have also impressive input and output, sort of that come along with input and output facilities, sensors and actuators that computers don't have. I mean, you can plug things in, of course, but they're not integrated in the same way into the information processing. Also, the neurons, although they're slow, they make many connections. So they have advantages on other axes. They're also much more energy efficient, as I alluded to, than the computers. They also have the advantage of, depending on how you count, either billions or millions of years of genetic algorithms that have improved them. So for all those reasons, the brains have kind of a head start. And I don't see these new kinds of minds catching up across the board anytime soon. They can do some things better already, but as far as general purposes are concerned, it's going to be a while before that happens. And I think the real thing that will happen in the foreseeable future is this ecology of minds, where you'll have different kinds of minds living together, and I hope thriving together, but we'll discuss that next time, where what it's going to take to make them thrive together as opposed to fighting or sort of indulging in destructive behavior. Yeah. Yes. Yeah.
Are there other ways in which AI can be used to combat dystopia, like in which someone creating roles?
I didn't hear the question clearly. Can you repeat it?
Are there other ways that AI can be used to combat dystopia?
Combat dystopia. Well, this is impinging on the next lecture, but yes, I think well, let me give an example that grows right out of what I did talk about today, which is we have coaches here and things that tell us, that nag at us when we're doing bad things. And so if it's monitoring your chemical balances, and it'll tell you and give you warnings that
you're in danger. I mean, more sophisticated version would tell you and give you warnings that you're in danger of becoming addicted to something. Might also give you prescriptions for what to do about it, advice for what to do about it. So yes, I think the possibilities for man-machine collaborations, symbioses that benefit both are very, very real. And I hope that's the way things develop.
We're almost out of time, so we'll have a final question.
The true AI comes out in the near future, then we have the means of this test.
Question was, if true AI is developed, do we have a way of sort of recognizing?
Okay, I think so. Yeah, the question again, repeating the question. If true AI develops, will we be able to recognize it? I'm not sure what the definition of true AI is, but you can ask a related question, which is if somebody in this room or on campus is actually a zombie, so they're not a true human being, or that they're a machine or something thoughtless, so that's not conscious, would we be able to recognize it? I think so. And the reason is that consciousness and which is really a form of self-awareness, is a very, very powerful learning tool and adaptation tool. And I think to acquire truly human-like abilities to function in a variety of environments and situations, something like that will be necessary. So if some future AI that sort of walks like a duck and talks like a duck and waddles like a duck, where of course by duck I mean human, actually tells you that I have feelings too, and you should believe it. Yeah, that's I think.
All right, thanks very much, and thank you to the audience for your questions and participating. We have another lecture next week. It will also be both here, yes, and that's on Wednesday, March 26th. So,
Thank you. Thank you.
Pass